Hello everyone, in this video we'll learn how to use Code Composer Studio with an MSP 430 Launchpad. We will see how to install it and create a new C project. Then we'll create a simple C program in order to understand the menus and buttons of the CCS, as well as to see the representation of variables in memory. Then we'll learn how floating point numbers are calculated in order to be stored in memory. And in the final part of the video, we'll open an example code that blinks the onboard LED. Let's start by introducing Code Composer Studio. This is the definition that I took from the Texas Instruments website. Basically, CCS provides you the environment to develop your code, build it, and debug it. It's based on Eclipse software framework. You can download the latest version from this link, and latest version is 10.2 as of January 2021. I'm using an older version of the CCS 9.2. However, the properties that I show here are valid for newer versions as well. By the way, CCS doesn't require a paid license. After starting the installation, you have to choose MSP low power MCUs during the processor support selection, because we will be working with MSP 430 Launchpad. After that, you can connect your MSP 430 Launchpad via the USB cable, and you're ready to go. You can start CCS. At first start, CCS asks for the workspace directory. Default is OK, or you can change it according to your preference. This will be the start screen that you will get. Here you can watch informative videos and look up resources. During the first startup, CCS can update the software. Also, after connecting the Launchpad, it can update the firmware as well. Now let's create a new C project. Let's go to File, New, CCS project. Here we are going to select our target as MSP 430 G2553, and we are going to enter a project name, for example, my first code, and we are going to select empty project with main.c, and we are going to click on finish. Now we are ready to edit main.c. By default, the main function has this line, which is stopping the watchdog timer. And the first line of the main.c includes the MSP 430 header file. This file actually routes to the specific header file based on our selection in the beginning of the Create CCS window, MSP 430 G2553. There are two options for generating code, build and debug. Debug contains the build, so no need to build separately. For the debug process, you need to have the Launchpad connected to your computer via USB. Otherwise, you will obviously get an error. So let's disconnect the Launchpad, and let me try to click on debug. Click on proceed. You can see that we are having this error. Error initializing emulator, no USB FAT was found, and we have the same message right here. This is because I disconnected the Launchpad. Let me connect it again. And let me click on retry. Okay, now our code is ready to run. Now let's take a look at the menu buttons. Here we have our resume button to resume the code to be run on the Launchpad. Then we have the suspend button to suspend the code that's running, or we have the terminate button which stops the code from running, and we have the step into buttons, step into, step over, and step return. Step into executes next line of code. If it's a subroutine, only executes the next line. Step over, similar to above, if it's a subroutine, executes the whole subroutine and then stops. Step return completes the execution of the subroutine. And we have the reset button, which you can do a soft reset or a hard reset. And we have the assembly step into and assembly step over buttons, which are performing step into and step over in the assembly conversion of the code. The restart button returns the program counter to the beginning of the loaded program. Now let's take a look at how we can put breakpoints in the code. In the editor window, we are going to right click on a certain line where we want to set the breakpoint. And then we can click on breakpoint. And if you want, you can remove the breakpoints from the breakpoints tab and you can click on, for example, remove all. In the expressions window, we can observe the variables in the code. In order to do this, we are going to click on add new expression, and we are going to write the name of the variable to be observed. During the execution of the code, it's not possible to see the value of the variable, so either we have to set breakpoints or suspend the execution of the code manually. Local variables can be seen in the Variables tab. They are automatically included. However, if you want to see the global variables, you should add them in the expressions window. Now let's write a simple code piece. I'm going to declare an integer d is equal to 0. And then in the main function, I'm going to write integer a is equal to 1, float b is equal to minus 255.25, and character c is equal to lowercase c, and I'm going to say d is equal to d plus 1. And I'm going to write a while one loop, which is going to perform nothing, but it's going to keep the microcontroller alive. And we can delete this, return 0, and we can change this integer to void since it's not going to return anything. And we can save the code. By default, compiler optimization is on in CCS, register optimizations. Now we are going to disable it for learning the debugging processes. To disable it, we are going to right click on our project. We are going to click on properties, and in the optimization part, we are going to select off instead of register optimizations, and we are going to click on apply and close. This is going to allow us to examine the variables in the variables window. Now let's click on debug. Let's click on proceed. And now we can see the variable names. However, their values are not the values that we have identified, because we need to first click on resume. And in order to see the variables, we can suspend the code. Now we can see that variable a is an integer and has the value of 1. Variable b is a float and its value is minus 255.25. Variable c is a character, and here we can see 99, which stands for lowercase c in ASCII character table. ASCII stands for American Standard Code for Information Exchange. It has been used for electronic communication of text-based characters, and it was developed from telegraph code. And you can see that in the variables window, we can see the memory locations of these variables. So a is in this memory location, b is in this memory location, c is in this memory location. So let's click on the memory browser and see these destinations. For example, let's first write integer a's address, and we can see that in this address we have the value of 1. Let's go to the memory address for b, f6. You can see that we have a value of 4000 in hexadecimals. We are going to see how this negative floating point is represented in memory. And if you look at the memory address that the C is residing, that's C, we can see that it's hexadecimal 63, which is standing for 99 in decimals, and that corresponds to lowercase in ASCII table. Now let's see how the floating points are represented in memory. A binary number n with fractional parts will be formulated like this. N is equal to minus 1 to the power of s times 2 to the power of e times f. Here S is the sign bit, E is the exponential value, and F is the fractional part. And then the number N is going to be stored in the memory as 3 blocks, S, E, and F combined together. There are different types of floating point representation in IEEE 754 standards, like half, single, double, and quad. Single format is going to be used in our microcontroller, so it consists of total 32 bits. The exponential bias is 2 to the power of 8 minus 1, which is 127. We are going to require only 1 bit for sign. We are going to require 8 bits for exponential. We are going to require 23 bits for F, and a total of 32 bits. So now let's see an example to represent a floating point in half format. So our number is 107.25, and we are going to convert it into binary. So this is 107, and this is .25 decimal in binary. Our sign bit is 0 because we have a positive number. Then we are going to be normalizing the number so that the integer part will only have 1 digit. So this number is going to be converted into this, and we are going to say that we are going to multiply it by 2 to the power of 6. In order to calculate the exponent value, we are going to add the exponent to the bias. So our exponent bias was 15 and our exponent was 6. So summing them up together, we have 25, which is 10101 in binary. And then after normalization, our fractional part was this, which corresponds to this. However, we are going to add 2 zeros in order to comply with the format. Remember that in the format we require 10 bits for F. So here we have 8 bits, so we are adding 2 zeros after those 8 bits, which is not going to change our number. Then we are going to represent our number as S, E, F connected together. So our sign bit was 0. Our exponent was 10101, which is this part. And the rest is the fractional part, which is this one. So if we convert this to hexadecimal, we have 56B4 in hexadecimal. We had mentioned that we require total 32 bits for representing a floating point number in single format. And we are using this format in our microcontroller. So our word size is not enough to store the 32 bits because our word size is 16, because our microcontroller is a 16-bit microcontroller. If the data to be saved to the memory is larger than the word size, which is in our case, then the data should be partitioned. So there are two methods for this. Little endian representation, which MSP 430 uses, and we have the big endian representation. In little endian representation, the least significant bit parts are saved first. So let's have an example. If the number that we need to store is CABF 4000 hexadecimal, the first memory address is going to have the least significant part, which is 4000, and the upper memory address is going to have the most significant part, which is CABF. Now let's go back to our example and see how we are representing -255.25 floating point number. So the floating point number that we wanted to represent was -255.25. So if you would like to see this number in binary, it is this is 255, and this is the fractional part. Now let's leave only one integer in the beginning, so we will have and our exponent will be 2 to the power of 7. So the exponent bias was 127 for single format, and we are going to add our exponent here, which is 7. It's going to be 134, and if we convert that to binary, we are going to have 1 0 0 0 0 1 1 0. This will be equal to our exponent. And before that, we need to have our sign bit. Since we have a negative sign, S is going to be equal to 1. Now that we have S and E, let's represent F. The fractional part was this part. Notice that we have 9 digits here. So we need to add 14 zero digits in order to comply with the standard. So we are going to have 14 zeros in our number. So this will be our F. So if we put it all together as SEF, it's going to be 1 coming from the sign, and we are going to have 1 0 0 0 0 1 1 0, and this is our E coming from this, and we are going to add the F here. So it's hard for me to write here, and if we convert it to hexadecimal, we are going to see that it's C37F4000. So this is our 32-bit representation of the number -255.25. Okay, so if we go back to Code Composer Studio, you can see that the floating number B was -255.25, and we have already calculated its representation in single point floating format, and it will be represented by C37F4000. However, since we had mentioned that MSP430 Launchpad is using the little endian representation, it's going to store the least significant parts first. So if you look at the memory address of floating point B, we see that its initial memory address is 03F6. So in 03F6, we see the LSB part of the number, which is 4000. And then in the next memory slot, which is 3F8, as you can see, it's highlighted, we have the value C37F. So these two memory slots, both 16 bits, are representing the floating point number B, which is -255.25. One more reminder about Code Composer Studio: you can use the Registers tab in order to investigate the registers of the microcontroller. For example, you can look at the port registers like P1 in, their values, P1 out, P1 there, and etc. Now let's continue to our lab example. Now let's create a new project by clicking on File, New, CCS project, and for example, let's name it Lab 1. And in the basic examples, we are going to choose Blink the LED, and we are going to click on Finish. Now let's observe the code. First, it automatically stops the watchdog timer, and then it configures P1.0 as output with this command, and then it declares the integer I, and in the infinite loop, it just toggles P1.0, so it will be 1 and then 0 and then 1 and then 0, etc. And it's creating a delay with a for loop which is doing nothing but decrementing from 10,000. So now let's debug the code. And let's click on resume. You can see that the LED is blinking. In the first assignment, you are going to decrease and increase the blinking speed of the LED 10 times by modifying the code. And in the second assignment, you are going to modify the code so that the LED is going to blink only n times instead of blinking infinitely. You can choose n on your preference. This was the end of the video. Thank you for watching. Bye.